Welcome. I'm Bruce Morey, Senior Technical Editor of Manufacturing Engineering Magazine, and this is another SME Media webinar. Today, our topic is finding success with composites through virtual manufacturing. This presentation is sponsored by ESI Group. ESI Group is a provider of virtual prototyping software and services. As a specialist in material physics, ESI has developed a proficiency in helping industrial manufacturers replace physical prototypes by virtual prototypes, allowing them to virtually manufacture, assemble, test, and pre-certify their future products. Composite structures are experiencing rapidly emerging opportunities. Automakers may consider them to extend the range of electrified and traditional vehicles without sacrificing strength, stiffness, or performance. The aviation industry is seeing an increased need for larger volume production of their components. Wherever lightweight but strong parts are needed, composites will be considered. Join us in this webinar as we discuss the challenges facing the product and process engineering for higher volume composite parts, addressing parts and components ranging from large structures to smaller components, from low production volumes to more mass-produced objects. Topics we'll explore today is 1. When part design and materials design intersect. 2. Composites value stream and life cycle. 3. Validating product performance with manufacturing intent. And finally, trends and industry solutions. An additional bonus, we will discuss examples of how top companies from automotive, aerospace, and marine are finding success with composite simulation tools. Our presenters today are Eric Kam and Arnaud Derames for composites. Eric Kam is the Marketing and Alliance Director, Manufacturing Business Channel with ESI Group. He supports extended reality solutions for product engineering, integration, virtual build and maintenance. A digital transformation advocate, he seeks to democratize simulation technologies in CAE, FEA, and CAD. Eric is a longtime member leader of SME technical communities with the BSME from Michigan Tech. Dr. Arnaud Derames, PhD, is the Innovation Discovery Manager with ESI Group. He is a CAE researcher in composite manufacturing with decades of experience. He holds a PhD from ENS Des Mines de Saint-Étienne in mechanical engineering with a concentration in fusion process simulation, including fiber bed deformation with a fluid-solid coupling approach. Arnaud is leading composites innovation and services for the company. He develops software prototypes, investigates new physics, and integrates academic research into industry. In addition, he manages composite manufacturing engineering services in Americas for the ESI Group. Before I turn things over to Eric and Arnaud, I'd like to outline how the webinar will proceed and a couple of housekeeping items. On the right side of the screen, you'll find a question and answer box. If at any time during the presentation you'd like to ask a question, please type it in this box and send it along. Those questions will be answered at the end of the presentation. Should we run out of time, the questions will be sent to Eric and Arnaud and you'll receive an answer by email. Should you experience any difficulty during the webinar, such as a blank screen or a lack of sound, please use the Q&A box to alert us and we'll respond individually in writing with a suggested fix. That brings us to the final housekeeping item. Should you experience any difficulty such as this, the presentation will be available in recorded form at about 4 p.m. Eastern today. You may then watch the recorded version of this webinar at a time and place when you have more bandwidth. You may also watch the webinar as many times as you wish to catch details you might have missed or for any other reason. All you must do is sign in again using the credentials you used to join us now. You may even share those credentials with colleagues who might benefit from learning more about this topic. Now, let me turn the microphone over to Eric.
All right, thank you very much for that introduction, Bruce. As he said, my name is Eric. I'm joined here today on this broadcast by Arnaud. And what we're going to be talking about today is just give you some of our own observations and insights relative to the composites manufacturing industry and some of the things that we've been seeing going on and how the importance of predictive analysis of not just the performance of composites, but also how the manufacturing process is going to come together. And one of the things that we've noticed, especially about composite materials, is that it's almost impossible to decouple the performance of the manufacturing, performance of the composite body from the manufacturing of that composite body. because they really live right at that intersection of materials combining with the resin, with the fiber, and with the performance. It all has to come together in just the right way to get the right performance. So one of our goals at ESI is to really help people move away from reliance on physical tests and physical prototypes. And we really want to help people move forward in a fully digital engineering for performance, engineering for manufacturing, and realization of their new products, their new processes, without relying on physical prototyping. And one of the things that I've been learning a lot as I've been talking more and more with Arno about our industry is the fact that there is today, with most composite manufacturing, a still very high reliance on physical prototyping. That it's very uncommon today to run into someone that says they realize their manufacturing of their composite product without doing some physical trial and error, without bootstrapping together some sort of preliminary tool, some hand construction of the fibers and hand pouring and hand filling of the resin to really get those product qualities that they want. And if we want to move forward and start seeing more mass production of these composite, lightweight and super strong and very safe products, we really have to find a way to break that reliance, that crutch that's slowing us down of physical prototyping. So I've just got a couple slides I pulled together with some industry research. I grabbed this from a variety of sources on the internet, and one of them was talking about the role that composites play in aerospace. So on the left-hand side of the chart, you can see a little graph showing the range of composites being used in new aircraft at the time of their introduction or their launch or their first flight in the industry. So we can see that all the way back in the 1960s, people were already using composites as part of their aerospace construction. But at that time, the mass, right, the total amount of structural weight from the composites was down in the low single digits as far as percentages. And it wasn't really until like later in the 1980s and 1990s that we even start to see as much as 10% of the aircraft mass coming from composite structures. And in the early aughts, early 2000s, this millennia, we see the A380 was really one of those groundbreaking vehicles that had a high percentage of composite, really kind of almost a degree of magnitude increase over its previous predecessors. And at this time, you can see that maybe the A380, when it was released, had about 20% of its mass made up from composite bodies. But they're not making a whole lot of A380s. Even at the peak of A380 sales and deliveries, there were not so many of these planes being made. So if it was still a hand-built, handcrafted aircraft out of composites, that was something people could get by with. Now, as we move into some of these other aircraft, as we're seeing larger volumes of these mid-sized aircraft, so for example, the Boeing 777 and the Airbus A330, we can see that in 2019, between the beginning of the year and the mid of 2019, we already saw that the Boeing 777, while it might only be 10 to 15% of its mass coming from composites, we're seeing that their deliveries are 16 or more vehicles already delivered by the mid of the year. Right? Same for the A330, we're seeing 12 of those or more. So more likely that we're already seeing the amount of mass that's contributing to these aircraft and the amount of different parts that have to be constructed is increasing. Now, if we compare that to more recent vehicles, right, so we're talking about aircraft like the A350, which is one of the new flagship aircraft coming out of Airbus, the Boeing the Boeing 787 Dreamliner, their mid-year deliveries were already topping 59 and 43 respectively. That means that there's going to be more than 100 of these aircraft being built. And that is 2 degrees of magnitude larger than what we were thinking about construction of the A380. If we talk about the latest generations of long-time aircraft like the A320, which of course is not just the 320 aircraft itself, but the 319, the 320, 21, and 22. All of those aircraft have 15% of their mass made up from composites. But the A320 Neo aircraft, that was already seeing more than 100 aircraft shipped between the beginning of 2019 and the middle of the year. So that means that a lot of the old rules of thumb that we might have had regarding composites manufacturing, that it's kind of a handcrafted, craft-built industry, is already shifting towards something that's bordering on mass production. Now, I know that sometimes when we talk mass production, and I know that when we compare automotive productions to aerospace production, a lot of times people say it's still a small volume, right? A typical automotive plant is finishing 1,000 vehicles in a day, right? And a typical aircraft has yet to see 1,000 aircraft being shipped in a year. But some of the new aspirations of the industry when it comes to the future of flight, the future of aerospace and aviation, we see already at last year's CES, I saw at least about 10% of the show floor in the automotive and the transportation area at CES last year was dedicated to Bell Flight, and they were showing off their Nexus Air Urban Taxi concept, a vertical takeoff vehicle that they're promising maybe someday will be the Uber of aircraft, a way to ride share and get airborne transportation mobility down to anybody who has enough time to load an app onto their phone and schedule themselves a ride. Now, maybe that's just a few years away still when you talk to folks about the reality of that. But what that means is that if we're going to turn the corner and start delivering and start seeing this urban air taxi and personal air mobility happen, we're going to move from traditional volumes of aircraft where we're talking about high double-digit volumes or hundreds of aircraft a year. Now we're talking about the potential for thousands and tens of thousands of these aircraft having to be manufactured each year. And that's going to mean a land shift is going to happen in the composites manufacturing space. Now, somebody told me recently when I was at West Tech, which was the SME event on the West Coast this year, we were having a steering committee meeting between ourselves and the smart manufacturing community. And at that show, one of the people there, one of the leaders of the community, pointed out that this air logistics, this idea of having drones delivering your Amazon for you, your Domino's for you, that this is really going to probably be the first major shift that's going to happen before we can realize these air taxis. And we're talking for them hundreds of thousands of potential aircraft a year, carrying around anything from a 25-pound to a 75-pound payload. And that's really going to make the composites manufacturing industry really have to step up their game in their ability to automate and mass produce those types of products. Now, a lot of the folks I talk to in automotive, they say, well, you know, composites are cute. They're really nice for those niche vehicles. You know, something we sell on the volume of a Corvette, something we sell on the volume of those Vipers or those GTs, right? Those vehicles, sure, we'll make them out of composites. But in fact, we're seeing a high volume of composites in mass-produced vehicles today. Take, for example, on the left-hand side of your page, that's an image that, again, that was someplace, I got that off of, I can't even read the slide anymore, but that's a GM slide, and that was from the GMC Sierra, where their new boxes on certain of their vehicles are heavily made up of a mix of materials, some composites, some glass-reinforced composites. We're also seeing some, I think there's some SMC in there, and some metal, right? So we're seeing these pickup trucks, which are probably one of the leading sectors of the automotive personal mobility market, really starting to grab onto the value that we see from composite manufacturing. On the right-hand side, you can see the BMW i3. That's a mass production vehicle that is a majority composite vehicle. And a lot of the benefit of having that vehicle made out of composite is, again, this idea of for every kilogram of reduction in my body weight, that's a few more kilograms that I can pack in of lithium-ion batteries to extend the range of that electric vehicle. So one of the things that we're seeing, as far as the overall trend that's leading to this growth in the composites manufacturing market, and that slide keeps on skipping ahead, is that the previous barriers to wider adoption are shifting. That we're seeing that there's an there's an increased need for composites in the mass markets, whether it's mass market aviation or this automotive scale of manufacturing. We are also seeing that the cost-benefit ratio of making things out of composites is increasing. It used to be in an internal combustion car. People might say that the value of, say, shaving a kilogram off of the car is approximately 50 cents to $1 per kilogram of overall value of that savings to the benefit of the consumer and the person we're selling that car to. In the aviation industry, for every kilogram they're able to shave off of that airframe, we're talking about $5 to $50 per kilogram of that value. And what we're seeing is that the convergence of those two numbers getting closer to each other, that now in the automotive industry, as we're moving towards greater electrification, there's much more consumer, there's much more financial benefit to the car maker for shaving that weight. So let's consider first this idea of how we engineer, how we develop new products and new programs when we know they're going to be made out of composites instead of your traditional metallic materials. When you take a look at this process design, we're going from, on the left-hand side, the initial product concept or product design, then the normal materials selection, and the engineering of what is the intended performance criteria, how strong, how stiff, what does this product need to do its job right. Then normally we would go into doing some manufacturing planning, manufacturing engineering, do some piloting, do some prototyping, evaluations of that, and then we would start testing to see if the thing that we made in fact delivered a makeable product. There's supposed to be some animation builds there, but somehow, let's see if they will actually build up. There we go. So one of the things that would happen in a conventional product development cycle is that occasionally, even though you've engineered what you thought was a perfect composite part. So in the bottom of this illustration, we have a product design from the Nakashima Propeller Company who had this idea that they wanted to take these large marine shipping propellers and start manufacturing them out of composite materials. They came up with a product concept. They started doing some math-based evaluations of whether or not that would give them the performance that they wanted to achieve, and then they set out to figure out how they're going to make that propeller. And it turns out that when you start doing this manufacturing engineering, you might find out that the way that the fibers and the resin interact with each other does not end up being exactly what you envisioned for the original product design. And if that happens when you're doing your manufacturing piloting, you have to go back to the drawing board and redesign your product to account for what might really happen in manufacturing. So then they do a couple of iterations that way, building up these propeller blades by hand, manufacturing them in a manually controlled process, cutting them open to see if they actually delivered the characteristics that you wanted, and lather, rinse, repeat. Then you go into now mass producing these propellers. So now they have to deliver at least 3 or 4 of these propeller blades per their products so that they could actually have some physical testing. So in that color illustration you see underneath the little lightning bolts there, you can see where they're doing some physical testing of that propeller to see whether or not it gave them the performance that they wanted. Did it have the right thrust ratio? Did it have cavitation issues? Did it make for a noisy propeller, transitioning noise and vibration down the shaft of that marine craft? Then, if something happens bad in the testing, Then they might have to go back and rethink the manufacturing, which might make them have to go back and redo the product design. And then finally, they get a propeller design that they think is okay. Now they move from this manually handcrafted, layer by layer put together by an individual, and now they start thinking about mass producing it, and they could still run into some issues where the production tooling and the production process don't deliver what they had earlier tested. And they might have to go all the way back to the drawing board and rethink their process. So this is the way composites engineering has been done for, well, we saw all the way back to the 1960s when people were starting to put composites into aircraft. And it turns out one of the things that we want to really help people optimize is to help them recognize earlier in that product development process that there's something wrong or something that could be improved with the design. So what we're looking at from this chart is that if time is on that axis going from left to right, our ability to influence the performance of a product, our ability to influence the manufacturing, the performance, the cost of that product, that influence is very high very early on in the process, and it's relatively cheap to achieve that influence. But as time goes on and as this program or this product development process advances, we do find that it's more expensive to try to influence those product changes. And in some cases, this might mean that we have almost no influence left by the time we find out that something is wrong, right? So one of the things that, I showed that slide of the BMW i3 earlier, a lot of the product designers there have now thought that maybe it wasn't quite the right price point for that vehicle to go 100% composite, even though it did extend the range, because it was still too expensive to produce that component. So what we're trying to do is we're trying to help everyone optimize their product performance life cycle. That we recognize that one of the ways that you try to, you almost have to cyclically or simultaneously address product design, materials engineering, and process. So one of the things that we learned from our discussions with Nakashima is that they recognized that using digital prototyping allowed them to predict how the carbon fibers are being impregnated with resin throughout that manufacturing process. And were able to quickly find out if that gave them the performance results that they were really looking for. And that really allowed them to streamline their product development process because they no longer had to make every blade by hand, cut it open to see if it was actually getting manufactured properly, and then repeat that process so they could start doing their physical testing. Instead, they were able to achieve that all digitally. So just a quick overview of the different types of composite processes that we're going to focus on today. We're focusing on CFRP, which I believe is carbon fiber reinforced plastic methods. Yeah, Arno whispered me the correct pronunciation of that. So there's two types of processes that are commonly used in this kind of manufacturing operation, and many of you on the webinar probably know this better than I do, but we'll just go through it anyway. First thing, there is what we might call pre-pregged or pre-impregnated product, where we are taking sheets of fibers that have already been impregnated or already been wetted, if you will, with the resin, and those are stored in big sheets of rolls of the pre-preg material, and those are kept at a certain temperature and certain condition in order to prevent them from curing and solidifying into the final product. Then there is the liquid composite molding, which you might know by RTM, which is resin transfer molding. Then there is compression resin transfer molding and vacuum-assisted resin transfer molding, of different ways of trying to infuse dry fibers or dry fabric sheets with a liquid resin in order to get that process. Now, one of the things about the composites that have been historically used in broader applications up until now, a lot of it was in this pre-preg category, but unfortunately those processes are typically kind of manual processes where a human being is taking that sheet of material, they are pushing it and pressing it down into a mold, pushing it into a tool, and running at lower production rates, right? Now, what's nice about this particular type of process is that it doesn't necessarily require that much complex tooling, right? People are normally kind of taking these sheets and pressing them into shape, but not using mating, solid upper and lower tools necessarily. And they were also nice because they were able to control this curing process in an autoclave so that the curing and the cooling process could be done well controlled. This was very nice for some of our larger applications and low production volumes of certain composite parts. However, one of the challenges that we face is that these processes that require this long-term temperature regulation, whether it's keeping these fast-curing pre-pregnated sheets at the cool temperature so that they don't cure ahead of time, then that just means for a long time we're storing those sheets in giant refrigerators and freezers in order to prevent them from quickly aging or curing to their final strength characteristics. On the other hand, we have materials that have to sit inside of autoclaves for a lot longer to reach an elevated curing temperature, and those parts are going to also require a long production time. So as we've been trying to ramp up and reach larger volumes for these pre-preg type processes, it turns out that the material science folks that are working on these new processes are always trying to balance the challenge that the materials that we use to cure faster, to reach higher production volumes, these materials are rather volatile. They're just going to change in their chemistry makeup over time if we don't control their temperature properly. Right? So all of these materials that help us reach higher productive rates are going to be a bit more volatile. The materials that have more stability and less volatility as far as their temperature-controlled processes, well, those processes just take longer. You have to let them sit in that autoclave that's illustrated on the left hand of the screen much longer. So it turns out that processes that are well-suited for mass production are not these processes that are highly reliant on manual control or this regulation of temperature over long times. We need processes that are going to be a bit more automatable, where we can try to, through process control that curing process a bit more finitely than the way we normally had to for these other processes. Another thing is that some processes are just not practical for very large parts. You might not be able to tell there are people in that top illustration and that bottom illustration. Those are large what do we call those? Those are the windmills, right? So this would be electric air farm, right? Or electrical, it causes cancer. I'm sorry. These are wind turbines, right? And these are the blades of a wind turbine that you see on the top of the screen. On the bottom of the screen, that is a wing construction for one of those Airbus A380s floating down the river. Also, there are people in there for scale. But these things are just not appropriate for these processes where we would have to build large mating tools that would control the forming of dry fabrics and the attempt to impregnate them with wet resin. And instead, these products are more suited for the processes where we don't have to try to have mating tools. We don't necessarily have giant autoclaves the size of that ship. So we're taking those and making those out of materials that cure at more controllable, easier to reach temperatures than what you would normally need an autoclave or specialized tooling for. So when we think about this product performance life cycle, we do have to make those decisions about the materials that we select and the manufacturing processes that we're going to use to develop them. We have to make those decisions very, very early. That it's impossible to design a brand new product with the intent to make it out of composites if we have not already validated or have already knowledge, confidence, that the manufacturing process is even going to ever deliver those products to us, right? So if we're going to mass produce something for Airbus, right? So this is, I believe, this is a section from a wing front of an airplane. Is that correct? A wing?
Yeah.
Right? Reinforcement strut, if you will. And so this would be the rib cage of the wings, if you could imagine. And these are going to be made out of flat patterned material that would be pressed into its relative shape, and then later on, there's supposed to be an animation build there. I love it when a plan comes together. There we go. Right? So for example, if this was the product that we were trying to manufacture, and we found out that the planned manufacturing process of taking that flat pattern blank that you see on the left-hand side or in the center of the screen, if the forming of that flat fabric and pressing that down created all of this wrinkling and gathering in the corners, then that would have a detrimental effect on the end performance of the product if we had not planned for that. So in order to optimize that, somebody could come up with a new pattern for the way that material shapes around the corner. Now it has an open corner design, and hopefully that prevents the wrinkles in that area. But what if that closed corner was a critical attribute of that product in order for it to do its job? So whether this is a section through a wing, whether this is part of a reinforcement for a car or an airplane or maybe for one of those drones, we really have to know, is it possible to redesign the product to accommodate this manufacturing mitigation? Because if it's not, and we know that there's wrinkling in the corners, we might have to totally rethink our entire manufacturing design as well as product design. So here's just a quick simulation prove-out of the forming of a wing box section. So if this is a wing box section for an aircraft, we want to be able to validate whether or not the tool design for forming this box section is going to allow us to reach the appropriate shape of the product as designed, given the fact that we have to take dry pieces of individual plies of composite material and get them to form without having that buckling and wrinkling in its shape. That was a simulation with the tooling visible. Now we've just made the kind of hidden that tooling from you so you can see a little bit better. But in this case, we're able to validate whether or not the product characteristics, the shapes that people wanted, and a critical thing about carbon fiber reinforced materials is that not only is it the shape of the outside of that product, but also the alignment of all of those individual fibers that are woven through that entire product shape. So it's those individual plies of that product weave in addition to the resin that delivers the final product characteristics. And we need to make sure that those things all line up properly. So it's important for us, if we're creating new products, that we do validate those manufacturing processes before we get too far down that product development time cycle. Because it might get too late for us to try to rethink what this wing box looks like if in fact we can't make this out of, I was lying earlier, that's thermoplastic, thermoforming sheets, right, as opposed to dry fibers. So this would be a pre-pregnated process, right? But in this case, you can definitely see that that wrinkling, if that's going to affect my product performance around the edges, I would have to account for that in the product design in the end. So the draping and the forming of these either pre-impregnated sheets, or if this is with dry fibers, dry sheets, it's really important for us to know that we're delivering the final product characteristics based on the natural tendency of these dry fibers to orient themselves or to create shear in those fiber weaves. And this is a critical part of every new product design. And we have to make sure that we can prove that as early as possible. So in this case, Airbus and the Eurocopter projects, they were taking a look at how they could try to use this is a dry fiber process, right? That we're going to later take these dry fibers and try to impregnate them with the carbon or with the resin, and we want to make sure that prior to that impregnation, we already know what are those sheets, what are those alignments of those fibers going to be like inside of that structure. So here's another example of just how we can use analysis, computer analysis to predict the behavior of those sheets during the forming process. So in this case, we have a series of dry fiber weave. Why is that running? We'll try that again. And we're going to fake it. The video is not happening right now. So just taking a look at this still image, the idea is that we want to validate in this first step of the manufacturing process what's going to happen as we close the tools on top of those dry fabric sheets. So in this case, we can see already that around the perimeter of this part, we have these two straight, or not really straight, this little saddle shape here, that are helping control how those individual sheets of dry fabric are going to be pushed down into that cavity as the tools close. And what we want to look out for is in this case, now we see it, we want to see how much are those fibers shearing relative to each other during that closing operation. Are we seeing that there's any excessive amount of shear, because that's going to change the alignment of those carbon fibers, and those carbon fibers might not be aligned exactly the way that the product engineers originally anticipated when they engineered this product. And for those minor variations in the alignment of the sheet, we can certainly see different performance of that product. So really, the thing that we want to consider is, what's going to happen when we close the die? Is there going to be problems with draping? Is there going to be some problems with the way those fibers maintain their alignment? I mean, in a worst case scenario, you could even have maybe some uncontrolled movement of those fiber sheets where they could actually double over and wrinkle up inside of the tool, and that could prevent full closure of the tool and therefore prevent us from getting the appropriate infusion characteristics and the proper thickness distribution that we were counting on. It could even keep the tool from closing and might cause the whole part to not be completely manufactured the way we intended. So once we take those fibers and we've now closed those fibers and those sheets inside of the tools and given them the general shape that we wanted for the process, now we want to evaluate and prove out how is the resin going to infuse and wet those dry fibers in order to give us our finished product. And so we always have to take a look at what is going to be the filling time. So how fast can we push that resin inside of the die cavity, and will it fill completely before it starts to cure and solidify in such a way, right, form those new polymerize, right, that it's going to change from being two individual materials in the resin and actually come to a new polymerized material that could become too viscous to actually flow through those sheets appropriately. Also, we need to make sure if all those fibers in the component are fully reached and fully infused with the resin in order to get the right product. And this combination of looking at how it fills, how it cures, and the temperature reached will be able to have some confidence that the dry fibers are now properly aligned during the filling, wetting, and the curing of those fibers. So for these large dimension parts, it can become really critical to be able to predict, are we maintaining that full flow of the resin throughout the product? Are we able to predictably maintain the right pressure and the right curing profile? So again, we're going to cross our fingers and hope these videos run properly. So here's a video of the simulation of the filling factor. So this is just showing how the fluid filled up that entire cavity where we have now the dry fibers. So the things we're looking out for is, are there areas in this product that are not properly being reached by all of the resin? Is it not getting filled appropriately? This one would be the characteristics of curing. So now, as that resin is flowing in, are we seeing some of that fluid polymerize too early, creating potential, think of it as islands or little rocks in the stream of that fluid flow, where an early polymerization of that resin could in fact block the planned flow or the future flow of that rest of the wet resin into that structure. And that could also change our ability to have confidence that we're getting the product characteristics we want. And this is a quick view of the pressure of inside of that tool as the resin is being pushed through. Because in this case, if we saw some of that early polymerization, that would cause the pressure to climb inside of the tool as we're pushing the resin in. And once the pressure reaches certain thresholds, we lose our confidence that the fibers are going to stay the way they're supposed to during that infusion process. And this is just a top view looking at the temperature, right? So we're seeing how does the temperature propagate throughout that, because in fact the curing process, some of these resins are curing exothermically. They're giving off some heat. We're also applying some heat to try to get some curing. And this temperature distribution can help shed light on our confidence that we're getting a fully cured, fully formed product at the end of the process. Then we think about the rest of that curing process, the maturing of that process, if you will, the finished aging of that process, to make sure that it is in fact curing fully to the final strength characteristics that were part of that engineering design. And this is really our way of being very confident that not only was this a highly performant, lightweight product that we saw fit to plan in the assembly of our new aircraft, of our new automobile, but one that we feel is reaching the right performance. And this is what Nakashima was able to do in order for them to be the first people on the market globally to bring a fully composite marine propeller or commercial marine propeller to market. Right? Prior to that, no one was building propellers at this scale from composite materials. And as a result, they're able to make a stronger, more performant, more quiet, and more efficient propeller because of the characteristics of the composite parts that they're manufacturing today. Somewhere around, I think they said it was going to be somewhere around like 10% more quiet. It was going to be like 40% of the overall mass. And it was going to reduce their overall fuel consumption while making a smoother, more high-performance ride in their marine craft. So our goal has been at ESI to provide tools that allow people to engineer their products throughout this entire cycle, considering not only the performance of the products, but what's it going to be like when we try to form the part, infuse it with the resin, cure it, and also be able to predict, are there any sort of distortions caused in the part as it completes the curing process and reaches that final performance characteristics. And we see that this is really critical for as we see industry move forward and try to invent products that didn't exist before. In this picture that's going to disappear in a short while, people are already talking about this idea of these autonomous electric taxis, electric shuttles moving around the city. And these things, in order to be as performant as possible and as efficient as possible, manufacturing out of composite materials is looking like a good way to go. So we've had recent success where people have been using ESI composite engineering products in order to properly predict that this was a feasible product design for this body side of their bus that they wanted to manufacture. And in this project, they were able to fully simulate the RTM process that let them secure the bus design and optimize their process. And that way, they're able to know not only the manufacturing process parameters, but also things such as the injection time, the pressure, and the mold, and they're able to fine-tune their process design to have a fine confidence and a high level of confidence that they could mass produce this vehicle for their customers. So that's what we've been doing here at ESI Group and how we've been trying to address, well, not only composites, but throughout the entire manufacturing, whether it's automotive, aerospace, marine, or energy industries, helping people design products and conduct design checks of their processes. Replace the tests that are normally used to validate or certify their products, and replace the need for prototyping products or prototyping tools in order to make smarter, more informed engineering decisions to make your prototypes more smart. And we've been doing that through different ways of helping people model their individual processes, whether that's the manufacturing process or how that product is going to behave in its final end-user performance, and trying to encourage the modeling, collaboration, and experience of those products well ahead of time. And that's what we've been doing in composites, and at this time I think I should probably stop doing the gabbing and open up the microphone for any questions that people might have.
Thank you, Eric. That was very fascinating. And an interesting introduction to composites.
Thank you. So let's see, I think we saw, I'm looking at the questions board right now, and there was a question from Paul Kumler from KTM Solutions, and wanted to know about the general aviation market because Beechcraft is using composites in their Starship and some of their other products. And the question is absolutely, right? Courtney's typing in what I'm saying here, so I got to be careful. But of course, the general aviation market, these different manufacturers at the scale of Beechcraft, scale of Gulfstream, and some of these other manufacturers, they've been using composites for quite some time. There's still, quite many of them are still operating on that scale where they're not using highly automated processes. In fact, in SME right now, we've been talking quite a bit about forming a new technical working group inside of the composites manufacturing technical community to address this challenge of how do we further automate and optimize that composites manufacturing process.
Thank you, Eric. I have a couple of questions myself that I've generated. One of the key questions with simulation is always material properties, and of course with metals and standard finite element analysis, material properties are well known. Can you comment on the maturity, if you will, of material properties when it comes to these more complex carbon fiber reinforced plastics and other composites?
So what type of material, are you talking about like the material properties we will need to feed our simulations, or are you talking more generally speaking about the final material properties of the composite parts?
Well, I'm thinking about the material properties in general when they're used in simulations.
Yeah,
usually there's a materials database.
Yeah, so
there's usually a materials database that the simulation tracks into. And I was just curious if you'd like to talk about that. Sometimes there's concerns in the community, and I'm sure that the maturity of composites are much higher than maybe some people think.
So the thing is that in the composite industry today, you still have a lot of material which are made for specific applications, and they are made for specific customers, for example. And so it's not that easy today to have well-known materials for which we have all the properties we can use. So you will always have some kind of material characterization to do to perform your simulation. We are working on building database to have this data, but when it comes to specific materials, you always have to do some characterization about your properties to be able to run the analysis. But one thing which is very important to understand regarding material properties of composite parts themselves is that when you are actually manufacturing or designing a composite part, you also are manufacturing or designing a material. Your fiber orientation, the number of layers you're going to use, how your resin is going to cure, and everything that's going to create a new material that is specifically designed for the parts you're actually making. And that's where we see that the manufacturing has a direct influence on the final properties of your composite part, and it becomes necessary to run manufacturing simulation in order to have the right properties in your final part to do your performance analysis.
Okay, so it's, I think what you're saying, it's more like kind of like a chicken and egg thing, or back and forth. You have to do some analysis and then do some real tests and some analysis to get the right material properties.
Yes, and that's one of the things that when we talk about this challenge that we have of doing predictive analysis when it comes to composites, is that many people have been doing their composites manufacturability analyses by more or less brute forcing, buying a general purpose finite element or computer-aided engineering tool and doing their own kind of custom development of a simulation process using a general purpose FEA tool. And if you take that new level of variability of that, I'm writing my own finite element analysis code in order to simulate this, and I'm also dealing with a question mark of how do I simulate the characteristics of these resins and materials? How do I simulate the characteristics of these dry fibers and these potentially pre-preg fibers? And what happens is a lot of people have been doing this math-based composites engineering, and they've been doing it by trying to optimize all three of those elements at the same time. How do I model and simulate it is one thing. How do I characterize these new materials? And of course, how do I design my products and my processes? And that's a lot of things to try to work on at the same time. And one of our focuses has been on coming up with a methodology where we can at least take some of those questions out of the way you're doing your simulation. So that now, through our approach, it's more capable for us to at least be able to easily define things that we can find to characterize about these new resins, right? So that when somebody presents to us, oh, we're thinking of using this new carbon fiber process invented by so-and-so using this new fabric and this new resin, at least we're able to say, for us to model it, we need to know what is its characteristics as far as its viscosity? What is its temperature profile for as it's polymerizing and changing through that temperature profile? How much is its degree of curing in a pure numerical sense? And that allows us to quickly adapt how we are doing our composites manufacturing processes through relatively straightforward and easy to characterize properties or characteristics. And unfortunately, you know, you hit on a really good point there, Bruce, is that there is no magic book, right? I've been coming out of a sheet metal stamping mentality for many years, and people just rattle off. You need to know the material's N value, its R value, and its forming limit curve. And for composites, it's not quite fully to that level of maturity, because for many people who've been doing their own kind of brute force bespoke methodology that they're coming up with on using general purpose software tools, there is no easy way for them to characterize all of those attributes. So we've been doing our part to try to make that a bit more straightforward for our customers and for industry to be able to more readily characterize these manufacturing processes.
So what you're saying is you shouldn't think of the lack of maturity as an impediment or a barrier to using this effectively.
That's correct, right? We are reaching points now where it is, you know, I wouldn't say it's easy or automatic. It's not something I can download from the internet immediately, but it is those types of things that at least we can start asking better informed questions to really let's call it, zero in on what we need to ask these new material suppliers about their new fibers and new resins. And certainly the questions that we've been asking, we've been finding more and more the vendors in the supply chain is well prepared to be able to answer those questions for us.
That's good to know. We had a couple of comments here. One is the Speech Starship is not in production anymore. This was an airplane produced in the 80s. My comment is more around the composites have been used in aircraft for years, and the general aviation industry actually pioneered this technology. Oh, I guess you might want to update your charts. I don't know. You might want to talk to that guy individually.
that chart was not necessarily pointing out to the ones that are still in production today. It was just talking about when composites were introduced and how widely they were used in those aircraft. And that's why I only really focused on a couple of those aircraft when I showed the chart, just to really focus on the ones that are hitting high volumes and, of course, are still in production today. Thank you very much for that input.
I think we're going to wrap this up. I think I can speak for a lot of people that this is a great presentation, very informative. Is there any closing comments you might want to offer our audience, Eric?
Well, I mean, one of the things is that it's important that we start asking these questions, and it cannot and will not see composites grow in industry unless people are really taking this kind of simultaneous engineering approach, that they really recognize that in order to validate the performance of these composite parts, they have to immediately start thinking about how are these parts going to be fabricated. Are they going to be pre-impregnated sheets? Are they going to be dry fibers infused with resin? And they have to start considering how do those alignments of those fibers, before they do a crash analysis, before they do a structural analysis, they really need to figure out how are those fibers going to get there. And if they're not ready to address that question, they are going to face really steep challenges in bringing those products to market. And we'd be happy to help everybody start addressing those questions as early as possible.
Thank you so much for your time, Eric and Arnaud. As this webinar has shown, there are many opportunities and benefits from the use of finding success with composites through virtual manufacturing. As always, SME and SME Media can help you keep abreast of developments in automation, robotics, and smart manufacturing on our website, advancedmanufacturing.org. And be sure to take a look at our upcoming events for the rest of the 2019 year and into next year. Thanks for joining us for this SME Media webinar. We hope you found it informative.
Thank you.